Okay, this is Evaporation by Gabriel, Brendan, Christian, and Ryan. So evaporation is the changing of a liquid into a gas, and predicting the rate of this evaporation can have many important real-world applications. And we can develop models for this rate of evaporation by using differential equations, which will give an accurate prediction. So using the SIMIODE article by Brian Winkle as a guide, the evaporation of 91% isopropyl alcohol solution with water is examined as an attempt to find an effective way to model the rate of evaporation. Rate of evaporation can be impacted by several factors such as temperature, surface area, humidity, and wind speed. So the rate of evaporation is a speed at which a liquid will be converted to a gas by the process of evaporation. Higher temperatures will cause a liquid to evaporate faster, and evaporation occurs at the surface of a liquid. So the greater the surface area of a liquid, the higher the rate of evaporation. Higher humidity means that the air already has higher amounts of water vapor. This makes it more difficult for evaporation because there's only so much water vapor in the atmosphere can hold. Higher humidity leads to slower rate of evaporation. And since evaporation causes an increase in humidity, rate of evaporation can slow over time over a liquid as humidity increases. But if there's wind can push the water vapor away, decreasing humidity with higher wind speeds, removing humidity faster. Therefore, higher wind speeds mean an increase in rate of evaporation. So evaporation is most frequently associated with water. It's one of the key components of the water cycle. The water cycle is a continuous movement of water on Earth happening in the atmosphere, on the Earth's surface, and below ground. The cycle is made up of three components: condensation, precipitation, and evaporation.
So the water cycle is when evaporation is heated when the water is heated to the point where it becomes a gas, and that's the evaporation. And the gas that comes out is called water vapor. And when this enters the atmosphere, it goes up, enters the atmosphere, it will cool down, and then 90% of the water vapor in the atmosphere is from this evaporation. So condensation occurs when this water vapor rises and then cools to the point where it forms the clouds in the sky. And as the clouds, the water is moved vast distances across like the world and in the sky and stuff. Precipitation occurs when the clouds release water as rain or snow, with the water eventually being evaporated again, and the cycle just goes on and on. And here's a picture of the water cycle. It shows that it evaporates, goes into the clouds, condenses up there, shows the plants there too, helps with that. And then precipitation goes down, the runoff off of like mountains and stuff forms big like lakes and puddles and stuff, and that's groundwater. And as you see there, a lot of that evaporates and continues the cycle. So the production of fresh water: when the salt water in the oceans evaporates, the salt is left behind, so just the fresh water vapor goes into the clouds, and that's where it comes down as rain after that from those clouds. Energy production: the steam engines are based on heating water until it evaporates and becomes steam, which spins those turbines that the steam engines have. And this process is used in nuclear plants and all around the world. Drying: to dry everything from clothes and sheets, it's heated either by the sun or other means like washers or like the dryers in your homes, and to remove water by evaporation as well. Sweating: when our bodies are too hot, we sweat to cool ourselves. The sweat on our skin is removed by evaporation, taking away our excess body heat. Cooling: evaporation is an endothermic process, so that means it absorbs heat to change from a liquid to gas. And when this evaporation occurs, the remaining amount of liquid that is not melted will be cooler. For example, soup will initially be steaming and very hot, but over time it'll cool and stop steaming. And then because enough heat will have been absorbed by evaporation, that is too cool to keep evaporating.
So when studying evaporation mathematically, you can use differential equations, specifically the three listed below, which is negative k VT, negative k VT squared, and negative k AT. In all three of these equations, VT is the volume at any given time. So the volume of, specifically in this experiment, it would have been isopropyl alcohol, but it could be water at any given time. And AT would be the cross-sectional area exposed to the air. So the surface of the water, the surface area. And solving specifically the first equation, you get VT equals A e to the negative KT. And when things are held constant, such as temperature, pressure, and the surface area, you can get the solution of that and use it to graph the volume of alcohol in the dish over time. So from the SIMIODE article, we're given these two sets of numbers. The first one, they used 3 different Petri dishes. So they measured those out in weight and then diameter so that we could get the diameters for the cross-sectional area. And the mass is to make sure we can account for the overall mass when we're subtracting from how much it weighs. And then the second figure is just a portion of the data taken from the medium dish from 0 to 2 minutes and how much the entire thing weighed, or how much isopropyl alcohol was in there. So if you take the full results from the medium dish, which are given in the SIMIODE again, you're given this line, which is a bit more linear than we had expected, but the experiment only ran for approximately 30 minutes, and there was many data points taken within those 30 minutes. So I think if it was given longer time, it would come out more exponential. So in conclusion, we researched the evaporation and the factors involved, and we determined that different differential equations can be used to model the evaporation. We looked at the data given by the SIMIODE article that showed the evaporation of 91% isopropyl alcohol on the Petri dishes, and this helped us find the rate of evaporation using factors such as temperature, surface area, humidity, and wind speed being held constant.